This is the second video in a series that I'm making to support a course in complex analysis taught at the advanced undergraduate level. The last time we went over the basic properties of the complex numbers, really in a rectangular setting, as well as some arithmetic properties. Here we're going to kind of revisit some stuff we did in the last video, but now in the polar setting. So let's first recall that we can view the set of complex numbers as a plane. We have a real axis and an imaginary axis. And that means any complex number can be written as a plus bi. So notice it's a units along the real axis and b units along the imaginary axis. So that means that's b times I to get onto that imaginary axis. Now, if we forget for a minute that we're in the complex plane and instead think that we're just in the real plane R2 and think about polar form of numbers in R2, well, then that should give us some motivation to hopefully develop something in parallel to that for C. So the way you want to think about it is having a line segment from the origin to this point A plus BI. That naturally creates an angle with the positive real axis, which I'll call theta. And then it also creates a distance from the origin, which I'll call r. So this r is the distance from the origin to our complex number, a plus bi, which I'll call z. So now let's notice that we've got some sort of relationship between r, theta, and a and b. And what is that relationship? Well, we can complete this triangle and put some measurements on it. So the measurement of the height of the triangle is b units. The base of the triangle is a units. So that tells us we have the following kind of translation. So first of all, we have A is equal to R cosine theta, just by standard trigonometric identities. And then B is equal to R sine theta. So now putting this together, we see that we can write Z, A plus BI, as R cos theta plus R plus I times R sine theta. And then we could also just factor this r out and we'll get cosine theta plus I sine theta. And I want to point out here that we might as well only take positive values for r, or I should say non-negative values. So r is a real number, which is bigger than or equal to 0. And furthermore, since sine and cosine are periodic, 2 pi periodic that is, we might as well take theta to be on an interval that has length 2 pi. That can be taken as 0 to 2 pi or as negative pi to pi, just kind of depending on the setting. Now, sometimes we will expand outside of that interval to make a calculation, but most of the time we'll stick to this interval. Okay, so now that we've got this developed, I want to develop Eulers' famous formula for writing this as a complex exponential. Okay, now we're going to look at Eulers' formula, which allows us to write this in a really powerful and succinct way. And that is, if we have z written in polar form as r times cosine theta plus I sine theta, then z can also be written in this exponential form. So it's r e to the I theta, where still r is a non-negative real number and theta can be taken to be here kind of or expanded as needed, as we'll see as we move forward. And while we're at it, I'm going to notice that r is exactly the modulus of z, which we looked at last time. Notice that r is the length of this hypotenuse of this triangle, which can be calculated with the Pythagorean theorem to exactly what we called the modulus last time. Furthermore, I want to introduce this notion of the argument of z, which we'll denote by argz, and that'll be this angle theta. So theta is known as the argument of z. Okay, that taken care of, let's maybe prove this little result, and we're just going to sketch out the calculation, using some stuff that we might know from Calculus 2. And in fact, we're only going to focus on this bit right here, where e to the I theta is shown to be equal to cosine theta plus I sine theta. Everything else will follow because we're just multiplying by r. So let's start off by recalling the series expansion of these three functions, the exponential function, sine, and cosine. So let's put that in here right here. We're going to recall that e to the x has a Maclaurin expansion of the sum as n goes from 0 to infinity, x to the n over n factorial. Cos x can be expanded as the sum as n goes from 0 to infinity minus 1 to the n over 2 times n factorial, and then x to the 2 times n. So notice it's an even function. And then we have sine of x is equal to the sum as n goes from 0 to infinity of minus 1 to the n over 2n plus 1 factorial x to the 2n plus 1. Okay, so again, that's just kind of recalling this stuff from Calculus 2. Now we're going to use these to directly come up with this equality that we need. So if we have e to the I theta, that's going to be equal to the sum as n goes from 0 up to infinity of I to the n theta to the n over n factorial. And now I'm going to break this sum into even parts and odd parts. So let's rewrite this as the sum as m goes from 0 to infinity of I to the 2m theta to the 2m over 2m factorial. So that'll be the even components. And then we'll have plus the sum as m goes from 0 to infinity of I to the 2m plus 1 theta to the 2m plus 1 over 2m plus 1 factorial. So again, these are the even parts, those are the odd parts. And by even and odd, I mean the even indices and the odd indices. And now I'm going to start to simplify this. So notice I can take this guy right here and almost rewrite it exactly, but now we'll have the sum as m goes from 0 to infinity of I squared to the m power using exponent rules. But I squared is -1, so that'll be -1 to the m power, theta to the 2m over 2m factorial. So just to reiterate what went on here, I replaced this I to the 2m with -1 to the m. Well, it's not really a replacement. Those are equal, given the fact that I squared is equal to -1. Now we can factor an I out of this, and that'll change that 2m plus 1 to a 2m, and we can do the same trick. So now we have plus I, and then the sum as m goes from 0 to infinity of -1 to the m theta to the 2m plus 1 over 2m plus 1 factorial. But now we have exactly our series expansion of cosine and sine. This is cos theta plus I sine theta. And we've established this claim. Okay, so now let's move on. Okay, now that we've developed Euler's formula for the polar form of a complex number, let's look at some nice cases of this formula. Starting with maybe the most famous, which is e to the I pi. So let's just go ahead and write this out. This is going to be cosine pi plus I times sine pi. So it's well known that sine evaluated in an integer multiple of pi will give us 0. So that means sine of pi is 0, cosine of pi is -1, and we've achieved this very famous formula. Now let's look at this one. We have the square root of 2, e to the I pi over 4. So that's the square root of 2 times cos pi over 4 plus I sine pi over 4. But let's recall that cosine and sine have the same value at pi over 4, and that's 1 over root 2. So that gives us root 2 times 1 over root 2 plus I times 1 over root 2. In other words, this is just the number 1 plus I. Now let's look at this e to the I 3 pi over 2. So that'll give us cos 3 pi over 2 plus I sine 3 pi over 2. We'll notice that cosine of a half integer multiple of pi is equal to 0. So that means we get a 0 here. And then sine of a half integer multiple of pi is either 1 or -1, depending on where it is. Here we get a -1. So in the end, we get a -I. Notice that all of this stuff makes sense graphically as well. Notice that e to the I pi would be like a pi radian angle, so it would be over here, that's -1. Likewise, this guy right here, e to the I 3 pi over 2, that would flip all the way down here to the negative imaginary axis. Okay, now let's look at this one, e to the I pi over 3. So that'll be cos pi over 3 plus I sine pi over 3. Got to maybe dust off your trig charts to recall what this is, but what you end up with is 1/2 plus I times the square root of 3 over 2. Now let's do one a little bit in reverse. So 1 minus I. Well, let's maybe sketch out where this is real quick. So notice 1 minus I will live right around down here. So notice the horizontal component is the same thing as the vertical component. It's just going down. In other words, the real part is the same as the imaginary part up to a sine. That makes this a 45-degree angle, or a pi over 4 radian angle, but it's actually negative pi over 4, or 3 pi over 4 if we were to measure it this way. Okay, so that means that this is going to be the modulus of this number, which is easy to calculate as the square root of 2 times e to this angle that we found, which maybe we'll use the version 3 pi over 4. So it's going to be I 3 pi over 4. Okay, so that's good. So now let's get rid of this and we'll move on. Now we're going to look at a nice application, which is deriving trigonometric identities fairly quickly. So let's start with the angle addition formula. So maybe we'll start with e to the I theta plus phi. Those will be the name of my two angles. So using this, so starting off with Eulers' formula, we know that that is cosine theta plus phi plus I sine theta plus phi. Okay, so that's a good place to start it. But then by exponent rules and multiplication of this exponential, we know that this is the same thing as e to the I theta times e to the I phi, because the exponents will add. And now we can expand each of these using Eulers' formula. So that's going to give us cos theta plus I sine theta times cos phi plus I sine phi. Now we can multiply this out as we multiplied complex numbers in rectangular form last time. So notice we'll get cos theta, cos phi, minus sine theta, sine phi. That will be the real part. And then the imaginary part will be equal to sine theta, cos phi, plus cos theta, sine phi. And now we look at the extreme left and right hand side of this equation that we've just constructed. And notice that we have the real part is cosine theta plus phi. And then the real part over here is this. And then finally, the imaginary part on the left hand side is this sine theta plus phi. But then the imaginary part on the right is this thing right here. So just maybe writing this purple one down, you can also write the red one down. We have derived the following identity. So cos theta plus phi is equal to cos theta cos phi minus sine theta sine phi. Okay, so let's do one more example that's similar to this. So for our next trigonometric identity, we're going to look at cosine 3 theta plus I sine 3 theta. And by taking real and imaginary parts, we'll have a formula for cosine 3 theta and one for I sine 3 theta. So let's notice we can start by writing this as e to the I 3 theta, which is the same thing as e to the I theta cubed. Again, using exponent rules, but that's exactly cos theta plus I sine theta quantity cubed. Now we can use binomial expansion, or maybe just multiply this out long ways if you want to. And what we'll end up with is cosine cubed theta, and then it'll be plus 3 times I cosine squared theta times sine theta. And then the next one would be minus 3 times cos theta sine squared theta. So that minus sign came from doing I squared because we have the sine squared. And then finally, we'll have minus I times sine cubed theta. And so that's from I cubed being minus I. Okay, but now we can combine real and imaginary parts. So notice the real part is cosine cubed minus 3 cosine times sine squared. So that's the real part telling us that this cosine 3 theta is equal to this stuff right here. Then furthermore, our imaginary part, so that'll be plus I times 3 cos squared theta sine theta minus sine cubed theta. So that gives us a nice identity for this triple angle of sine. Now you could write those all as 2 equations if you wanted to, but I'll just leave it like that and we'll move on. Next, we're going to look at a nice simple proposition about the argument. So first off, the argument of z times w is equal to the argument of z plus the argument of w. And next, the argument of z bar is the same thing as the argument of 1 over z, which is the argument of z but negative. So negative the argument of z. And this should be as long as z is not equal to 0, just for this bit right here. Okay, so let's look at this. So maybe starting with this one, let's set z equal to r times e to the I theta. We'll set w equal to maybe capital R e to the I phi. And our result is going to follow fairly quickly. So notice that argument of z times w is the same thing as the argument of little r times big R times e to the I theta plus phi. But that's going to be exactly equal to theta plus phi, which is the argument of z plus the argument of w. And this isn't strictly true because notice if we surpass 2 pi, something happens. So to be really careful here, we would maybe have to include the fact that we're working mod 2 pi. So what do I mean by that? That means that the difference between the argument of zw and this sum over here is a multiple of 2 pi. That's not so worrisome if they add up to something less than 2 pi though. Okay, good. Now let's work on these. Maybe I'll just prove this first equality. Maybe I'll just prove this one that I'm underlining in red and leave the other one as like a warm-up exercise. So let's first note z times z bar is equal to the modulus of z squared, which is a non-negative real number. So in other words, it's on the interval 0 to infinity. Maybe we could also write this as r bigger than or equal to 0 like this. But anything on the positive real number line is going to have an argument of 0. So that means we have the argument of z bar is equal to 0. But then expanding this out, we know that the argument of z plus the argument of z bar is equal to 0. But that's exactly what we need in order to have the argument of z bar is negative the argument of z. Okay, so let's get rid of this and we'll keep going. Now we want to look at what we've done with the polar form of a complex number and everything building up to this to quickly look at nth roots and nth powers of complex numbers and do nice calculations. So let's start by looking at a definition. So z is said to be an nth root of a complex number w if z to the n is equal to w. Now we've got this nice observation which says there are exactly n nth roots of w as long as w is not equal to 0. So let's do a little sketchy proof of this. So we'll start by writing w as r e to the I theta. And notice that we can change this to, instead of I theta, but I theta plus 2 pi m, as m ranges over all integers. Again, given the periodicity of cosine and sine. So now notice if we have z to the n is equal to r e to the I theta plus 2 pi times m, then that means that z could be taken to be r to the 1 over n times e to the I theta over n plus 2 pi m over n. Now, instead of taking all integers m, I'll only take the integers that will give us distinct numbers. And notice we'll start repeating again when n equals m, because we'll have a plus 2 pi in here. So that means I only really need to take the values of m from 0 to n minus 1. That'll give me all distinct nth roots of w. Okay, so these are the nth roots of w. Okay, so now let's look at some examples. Now let's use the result of that observation to do a couple of nice examples. The first of which is to find all square roots of the complex number 9i. So let's just recall that since we have a square root, there are exactly 2 square roots. That's how many we should be looking for. So let's start by writing 9i in its polar form. So notice that's going to be 9 times e to the I pi over 2. So why is it e to the I pi over 2? Well, I is this point up here. So the argument of I is pi over 2 because it's a right angle from this positive real axis. Now, if we want to find all square roots of 9i, that means we need to look at the equation z squared equals 9e to the I pi over 2 plus 2 pi times m. And then, since we have square roots, we know they'll be exactly 2 like we talked about before. That means m comes from the set 0 or 1. Okay, so now taking the square root, we'll get z is equal to 3, because the square root of 9 is 3. Then we'll have e to the I pi over 4. We're dividing each of these by 2, plus pi times m again, where m is equal to 0 or 1. So let's just put 0 or 1 here. So that gives us 2 values. We have 3e to the I pi over 4, and we have 3e to the I 5 pi over 4. So let's see what those would look like if we were to plot them. So there's our complex plane. E to the I pi over 4 will be somewhere over here. So we know the argument is pi over 4. So that's like a 45-degree angle. Here we've got pi over 4 here. So this would be maybe z, I'll call it z1 for my first root, and I'll call this z2 for the second root. So now where's 5 pi over 4? Well, it's pi over 4 plus pi. So that's going to be down in this direction. So it's going to be something like right about there. So this would be our point z2. The argument of that is pi over 4. Okay, so now let's get rid of this and we'll look at a couple more like this. So next, let's find all cube roots of 1 plus I. So let's first notice that we can write 1 plus I as the square root of 2 times e to the I pi over 4. Again, that's just from translating from rectangular form to polar form and then putting it in this complex number setup. Okay, so that means if we want to solve z cubed equal 1 plus I, then we'll need to look at the equation z cubed equals the square root of 2. I'm going to write that as 2 to the half just for ease. And then e to the I pi over 4 plus 2 pi m. And here m is going to go between 0 and 2 because we want 3 roots given that this is a cube root. Okay, so that means we have 3 roots. I'll call the first one z1. That will be 2 to the 6th. So that'll be 1/3 divided by 3. And then we'll have e to the I pi over 12. So that would be the m equals 0 case. Okay, now let's look at z2. So that'll be 2 to the 6th, and we'll have e to the I pi over 12, and then the m equals 1 case, which will be plus 2 pi over 3. Again, that's if we have m equals 1. And we obviously divided by 3 in order to solve this. Okay, and then finally, we'll have z3 will be the last one, which will be 2 to the 6th, e to the I, pi over 12, plus 4 pi over 3. And that's because here we're taking m to be equal to 2. Now you could combine these to simplify if you wanted to, but I'll just leave it like that. And to finish this one off, let's make a plot just like we did before. So let's see. Let's say we've got the circle here, which has a radius of 2 to the 1 over 6. So that means all of these roots will live on that circle. Let's say z1, notice the argument is pi over 12. So pi over 4 is right here. So it's about a third of pi over 4. So that's going to be right about here. So that's z1. Now what happens to this? Well, it's on the same circle, but the argument has increased by 2 pi over 3. So that's like 120 degrees. So that's going to put us like over here somewhere. So that'll be z2, and then we'll be over here somewhere for z3. Okay, so that looks like a good plot of these 3 points. Okay, so let's finish this off with some assorted examples, and then we'll end with some warm-up exercise. So for our first assorted example, we're gonna simplify 1 plus I to the 6th without like multiplying it out using the binomial expansion. We'll use this polar form. So let's notice that this is the same thing as the square root of 2, which is 2 to the half e to the I pi over 4 to the 6th power. So we've used this polar form of 1 plus I a couple times, so I won't review that. Now we can bring this 6 through here, and we get 2 to the 6 over 2, which is 2 cubed. Now we have e to the I 6 pi over 4. We can start simplifying this a little bit. So this is going to be 8 e to the I. Well, let's see. 6 pi over 4 is the same thing as 3 pi over 2. Okay, but what's 3 pi over 2 give us? That's going to give us minus I. So notice here's pi over 2, here's pi. 3 pi over 2 is down here, the negative imaginary axis. So this ends up being minus 8I. If you wanted to plug that into sines and cosines, that would be another way to do this. Okay, one more assorted example and then some warm-up problems. So for our last example, we'll plot this interesting set of points satisfying the following equation. We have the argument of z is equal to the modulus of z. Let's start by recalling that the argument of z is between 0 and 2 pi, not including 2 pi. It could also be between negative pi and pi, but having a negative argument doesn't really make sense here because the modulus is always positive. Okay, good. So now let's see what we've got. So let's make our complex plane here. And let's notice that the only thing that has a modulus of 0 is the number 0. And the number 0 also has an argument of 0. Anything along the positive real axis will have an argument of 0, but a modulus which is non-zero. Anything along the negative real axis will have the same thing. The modulus will not be 0, but the argument will be 0. Well, let's think about another point on this plot. Well, I think there's one nice that's right here, which would be the point pi over 2 times I. Let's notice the modulus of pi over 2 times I is the same thing as pi over 2. And the argument of I is pi over 2. So that means that this equation is satisfied. Then moving over here, we could have like this point down here, which is minus pi. So the modulus is pi and the argument is pi. Then finally, maybe like down here, we would have negative 3 pi over 2 times I. So we're getting further and further away from the origin. So that's going to give us a picture that's something like this. I think it's a nice spiral. You might say, well, where does it go? Does it continue on forever? And it does not. Notice it has kind of an open dot right here at 2 pi. And that dot is open because once we hit 2 pi, well, we're a real number again and the modulus is 0. So this would be the complete graph of the points satisfying this. Okay, let's finish this off with some warm-up problems. Okay, so I've cooked up a couple of examples in Mathematica that I'd like to show you for plotting in the complex plane using polar form. So we've got a pretty similar setup to what we had in the last video. So we set z equal to x plus iy just so that our calculations in Mathematica look like our hand calculations.
And again, we'll have a couple of tools that will be useful in addition to the ones that we saw last time. First is this argument function. So recall that the argument is the angle attached to the polar form of a complex number. And so notice it's just ARG. So if we take argument of 3 minus 4i, we get minus the inverse tangent of 4 over 3, which is in line what we saw in the main part of the video. Now, in addition to contour plot, which allows us to plot equations, we can plot inequalities with something called region plot. So let's see, we've got region plot. So this is the plot of the region, y less than or equal to x squared for these values of x and these values of y. This sets the axes on. So let's see what we get for that. So as expected, it's everything below the curve y equals x squared, including the curve y equals x squared. Okay, so now let's look at our examples. So let's plot all complex numbers whose argument is equal to pi over 6. So notice that's inside this contour plot. We've got argument equals pi over 6. Notice we need a double equal sign here. So let's see. Well, we get what's expected, which is a ray that makes an angle with the positive x-axis of pi over 6 radians, or 30 degrees. Okay, so now let's look at our next example, which is this inequality. So this is all values z, whose argument is between pi over 6 and pi over 4. So again, as expected, this gives us this slice of the complex plane. So the angle here is pi over 6, and the angle here is pi over 4. And here we used region plot. So now let's look at some little more interesting examples that would maybe be harder to plot by hand. So what about the region where the argument is equal to the modulus? And so recall that the modulus of a complex number in Mathematica is abs, so like absolute value. So let's see what we get for that. So we get this kind of half of a cardioid. So that's kind of nice. I'll let you guys think about how you could maybe get the rest of the cardioid out of this. And you can actually rewrite this using polar coordinates to see exactly why this is working. Again, I'll leave that as an exercise. Okay, well, let's look at an inequality. So let's say the argument is less than or equal to the modulus. So here we've got to use the region plot. So that's kind of cool. We get everything outside of the cardioid. And here are some more exotic examples. So let's look at when the argument of z plus I equals the modulus of z squared minus 4. So we got to use contour plot here. Well, notice we get these nice two little bubbles. So again, I think that's pretty cool. And now let's look at this example when the argument of z plus 2i is bigger than the modulus of z squared minus 2. So we've got to use region plot here. So notice we get two little bubbles, but now they're filled in because we've got this inequality. So I think it's interesting that the inequality in this direction where the argument is larger gives us the inside. That kind of makes sense because that means the modulus is smaller than something. Well, what happens if we were to switch this inequality around? Well, notice we get the outside of those little bubbles. Okay, so let's maybe change that back. And I'll leave you guys with some warm-up problems.
Okay, so I'll leave you guys with 3 warm-up problems. The first of which is to find and plot all fourth roots of I. Next, simplify this expression. Half plus I times square root of 3 over 2, all to the 5th power. And then finally, sketch the points satisfying this inequality and this equation. So we have the absolute value of the argument of z is less than pi over 3. And then here we have the log of the modulus of z is -2 times the argument of z. And that's a good place to stop.